exploring the process of developing a traffic sign recognizer using deep learning concepts. Ever wondered how machines identify and recognize things by themselves? We developed a model and created a traffic sign recognizer to show how machines get trained for the entire process. This video will cover every step throughout the process, digging into the basics and making it easier for anybody to understand the workflow. Before we begin, let's have a quick look at what we developed. Hi everyone, this is Fidenz Technologies, and in this video we'll describe how we developed a traffic sign recognizer using a convolutional neural network approach. The clip will further explain how we applied the fundamentals of deep learning to the space of traffic signs. Before we begin, let's have a quick look into the definitions of our fundamentals. Machine learning. Machine learning is the process where computers learn from data and use that knowledge to take action. Two examples of machine learning would be voice recognition and personalized website recommendations. Now let's move on to our next definition. Computer vision. Computer vision is a field of study that focuses on developing techniques to help computers see and understand the content of digital images. Facial recognition is an instance where we apply the techniques of computer vision. Moving on to the dataset that helped us host a model development. As explained previously, machine learning requires data to learn the patterns, so let's look into our dataset before stepping into the process. With quick research, we managed to find a dataset called the German Traffic Sign Recognition Benchmark to develop our model. For this, we performed an exploratory data analyze the data and move forward with clearer insights. Our trained dataset contained 39,000 plus images, whereas the test dataset comprised 12,000 plus images. All these images are classified into 43 classes. To make the learning more efficient, we normalize the dataset by transforming raw data. The goal is to train the model until it can recognize new types of traffic sign images. Let's move on to the next phase, the deep learning workflow. Our model generation approach consists of two fundamental steps. The first step is defining the model architecture with a set of hyperparameters, whereas the second step is constructing the model by training it against the training data set. The diagram explains how these fundamental steps are implemented in a deep learning development environment. As you may already know, the workflow of a deep learning application begins with an initial dataset getting split into three distinct subsets known as training, validation, and test. To begin the process, we define an architecture for the model with a set of hyperparameters, considering the type of problem we solve. Then, we use our training dataset to train this initially defined model and to obtain an improved version of it. Now, we apply the improved model to the validation dataset and check its performance by checking whether the model manages to correctly classify the inputs. The performance of the model is assessed using an evaluation metric. In our case, accuracy is the evaluation metric, although it can vary upon different problems. This is where the iterative cycle begins, where we can further attempt to improve the model by introducing hyperparameter and architectural changes to the existing model. The substeps of step 3 are repeated until we pick up an acceptable model. Once we have our acceptable or the final model, we use it against the completely unseen test dataset. This step provides us an insight into how our final model will behave in the real world. Model development, the iterative cycle. This was the most interesting part of the project, where we tried out different model training approaches to improve the accuracy. To be precise, we tried out 11 different models, but just to keep it short and relevant, we will be discussing only the models that made a significant impact on the accuracy of the final goal. If you are interested to know all the details, check out our blog post on this. You can find the link to that in the description. Model development was the longest part of our process, where we tried and tested several models till we achieved the desired level. Simultaneously, we used plots to interpret the results of each model throughout the evaluation process. Let's discuss our selected models that featured the milestones of the development process. Model 1. We started the process with a simple one-layer neural network where the layer uses softmax as the activation function. This is because our focus is on a classification problem. Apart from that, we utilized the atom optimizer with the intention of adding momentum to the optimization algorithm. This allows the algorithm to minimize the loss. We were able to achieve an excellent result from our first model itself, which was a validation accuracy of 90.16%. Model 2. Here, we modified our model by adding a strided convolutional layer, where convolutional neural networks apply a series of learnable filters to the input image. As a result, we improved Model 1 to eventually get a validation accuracy of 97.13%. Model 5. We further utilized max pooling along with strided convolutional layers, and max pooling essentially helps us extract the sharpest features in the image. With this addition, we witnessed a rise up to 98.83%. Even so, we noticed a difference between the training error and validation error, which is an indication of overfitting. Overfitting occurs when a model learns the detail and noise in the training data to the extent that it negatively impacts the performance of the model on real-world data. Therefore, our next challenge was to address the overfitting issue. Model 11. To address the overfitting problem, we used the dropout technique where random neurons are dropped from the network with a probability of p at each training iteration. We added a few dropout layers where necessary, and further utilized the services of max pooling and usual dense layers between Model 5 and Model 11. The end result enabled us to reach an almost perfect validation accuracy of 99.53%. Summary. As mentioned earlier, although the models with key turning points are represented in this video, we did a total of 11 models to achieve the final model. Here is the summary of the results we achieved during each model. The test drive. Now that we have finalized our model, it is time to test how it works with real-world data. For this, we used our test dataset, the data that the model has not seen yet. Following the test drive, the model managed to achieve an accuracy of 96.37% on the completely unseen dataset, reflecting a high robustness of our model for the production run. Feature additions for empirical issues. During the development process, the model was instructed to strictly output the designated 43 types of traffic signs. This means even if we input a non-traffic poster, the model will classify them under a particular category. To address this issue, we followed a methodical approach following novelty detection. Classes from 43 to 44 and added the unknown traffic sign as a class to the existing model. We further included a set of non-traffic images to our train and test datasets for training and testing purposes. With this development, the model was able to identify non-traffic signs and put them under class 44, which is the unknown category. Do it yourself. In order to use the model we developed, it is necessary to have an interface where it can be tested and used. To make it useful for everyone, including a less tech-savvy person, we created a handy web application that you saw during the start of this video. With this application, our trained model can be tested and utilized by anyone. Now is the time for you to test our model and experience the results of our developed model. Check out the DIY link in the description and do not forget to comment your thoughts and suggestions. Enjoy!